Now we're going to look at nuclear decay. As we go through this PowerPoint, be sure to look if you see my mouse cursor come on the screen. Here it is. I'm going to be pointing out some important points with my mouse cursor, so follow along and I'll highlight what I'm talking about. When we talk about nuclear decay, we're talking about really one thing, and that thing is radioactivity. This is a word that you've probably heard before, but you might not know exactly what it means. When we're talking about radioactivity or nuclear decay, anything that nuclear takes place inside the nucleus. Okay, the root word of nuclear right here is the same root word of nucleus. It's the same word. So whenever we talk about nuclear reactions, we talk about inside the nucleus. So if a nucleus is unstable, that means we describe it as it being radioactive. And since it's unstable, it's going to decay or undergo a nuclear reaction in an attempt to become stable. Okay, atoms like to be stable. It's less energy to be stable than it is to be unstable. So they're going to attempt to use whatever is less energy. And in their attempt to become stable, they undergo what we call nuclear decay. Now there's three types of nuclear decay. We have alpha decay, we have beta decay, and we have gamma decay. Okay, these are all Greek letters, so when you see them, if you see the Greek letter that it goes with it, and it looks like a funny English letter to you, that's because it's in a different language. It's in Greek. Okay, the first one we're going to look at is alpha. So each decay has what we call a decay symbol. This is something that we use when we write it in a nuclear equation, as you can see the example down here at the bottom. Okay, the decay symbol for an alpha is a helium nucleus. Okay, remember these are written in isotopic notation. What that means is we have our symbol here. In the bottom left-hand corner, we have our atomic number, and in the top left-hand corner, we have our mass number. Remember, mass number is protons plus neutrons. Okay, so your protons plus your neutrons give us our mass number, and we show that in isotopic notation in the top left-hand corner. So as you can see, you're using our symbol for helium because we have 2 as our atomic number. Anything that has 2 as an atomic number is automatically a helium nucleus, so we can classify an alpha particle as a helium nucleus. So if you look at the example here, we have radium undergoing an alpha decay, so radium, then we have our yields arrow. Remember, the arrow is kind of like the equal sign in math. It separates the left side of the equation from the right side. So if you look at the left side, we have our radioactive nucleus, which is radium. It is undergoing an alpha decay, and it produces an alpha particle, and then it transmutes, which means it changes its identity into a new element. So we went from an atomic number of 88 to an atomic number of 86. So we went from being radium to being radon, and that was through our nuclear decay, and we released an alpha particle to do it. Now alpha particles, they're kind of big, they're kind of heavy. Okay, you can stop alpha particles with a sheet of paper. So your skin actually stops alpha particles all the time. You're constantly stopping alpha particles. They got kind of low penetrating hour and low energy. But since they are a helium nucleus, they do have a mass of 4 AMU. Remember, AMU stands for atomic mass unit. So that has 2 protons, 2 neutrons. You add them together, you get a mass number of 4 AMUs. Since they're kind of big, if they ever get inside of a human body or inside of something that's living, they can do a lot of damage once they're in there. And a lot of the radioactive poisoning that you may be familiar with, you may have seen in movies or on the news or read about in books, a lot of that is due to alpha particles getting inside, and they cause a lot of damage once they're inside. But they have such low penetrating power that getting inside is very hard for them. And since it's a helium nucleus, it doesn't have any electrons, so you have 2 protons, which means your charge is positive 2. Okay, it's going to have a positive 2 charge because it has 2 protons and no electrons. The second type of radioactive decay we're looking at is beta decay. Okay, beta particles are essentially an electron. Okay, it's not exactly the same thing as an electron when you're thinking if you drew your Bohr diagrams or did your electron configuration. It's not exactly the same. This is an electron that's coming from from the nucleus. So you can think about it coming from the nucleus. The nucleus is shooting off an electron, and it's changing its identity when it does it. Okay, it's going to change the atomic number by 1, and since it's changing it by 1 in the opposite direction, we identify that by having a -1 there for its atomic number. And since it's an electron, it has 0 mass. Okay, its mass is so small that it's negligible. We can just ignore it. So here in our example, we have carbon with a mass number 14 undergoing beta decay, and so the carbon is over on the left side, our beta particle is over here on the right side, and it turns into nitrogen. Okay, and so when we look at the math of it, we can see that the law of conservation of mass applies to these types of equations. We have our atomic number 6 on this side, we have an atomic number of 7 plus an atomic number of -1, so it ends up equaling 6. So our atomic number is the same on the left and the right, and we'll hit that pretty hard when we look at the math of it. This symbol over here is just showing that it releases some energy. Okay, so you release some energy whenever you go through nuclear decay, and that's the whole point. You're trying to release energy to reach a lower energy stable state. Beta particles, you can stop them with a sheet of aluminum foil. They're going to go right through your paper, but they are stopped by a small piece of metal. So if you have aluminum foil and you make a hat out of it, your head will be completely protected from beta particles. Their penetrating power is moderate. Again, they can break through your sheet of paper, but they are going to be stopped by metal. They have about a moderate energy, and they have 0 mass. Okay, so when we look at a charge here, they don't have any protons, but instead, if we classify it as an electron and we say its charge is -1. Okay, so that's beta particles. Our last particle we're going to look at is a gamma ray. Okay, gamma ray is special because it is nothing more than like a beam of light. Okay, so our decay symbol is the Greek letter gamma. It looks like a fancy Y. Okay, so it looks kind of like a cursive Y right here, but this is really a Greek letter, and that's the letter for gamma. We can see, based on its isotopic notation, that it has no atomic number, and it has no mass. Okay, so our atomic number is 0, our mass is 0, and you can see down here that because the atomic number is 0 and the mass is 0, it has no change in what element or what mass number you are. Instead, it's just releasing a big thing of energy. So it's a high energy photon. Remember, photons are just particles of light. So gamma rays can be stopped by lead or concrete. That means they have very strong penetrating power. Okay, they're going to go right through your piece of paper, right through your aluminum foil, right through your water. They have to be stopped by layers upon layers of lead and concrete. They're very high in energy. They have no mass and no charge. Okay, so these guys are a little bit scary when you think about it. So when we look at our nuclear reaction examples, this is what you're going to see. You're going to see a element, and you're going to see that it's undergoing some type of nuclear decay, and you have to either figure out what type of decay it went through or what it turns into. So here we can identify what type of decay it is based on the particle. Over here at the arrow, you can see that it is a helium nucleus, and we know that a helium nucleus is an alpha particle, so we can label it as alpha decay. On the bottom one, we don't know what type of particle it is, so we have to look at the numbers that were given. We see we have a 91 on the atomic number for the left side, and it turns into uranium, which has an atomic number of 92, so we can show that the atomic number changed by -1, and we know that -1 is a beta particle, and so we can classify it as beta decay. To understand the math, you're going to have to watch the next video, so go ahead and watch that to really understand what we're talking about when we're talking about the change in the atomic number and the mass number.